Alright, this is our AP1 simple harmonic motion and universal circular motion, or uniform circular motion, springs and pendulums notes. So let's talk a little bit about springs and pendulums and how they'll fit in with this unit. We have to start off with some basic definitions. Periodic motion is when a vibration or an oscillation repeats itself over the same path. And so it's going to just repeat itself over and over and over again. A sine curve is a good example of this. A pendulum moving back and forth is a good example of this. So all of those are periodic motion. Simple harmonic motion is a specific form of periodic motion in which the restoring force is proportional to the distance from the equilibrium position. So we are going to deal with forces and positions, and we're going to talk about equilibrium as we go along. But really, simple harmonic motion is just a specific form of periodic motion. So objects that exhibit simple harmonic motion would be things like springs, pendulums, circular motion, and waves, which we will talk about sound a little bit in AP1. We talk about it a lot in AP2. We also talk about it in, we talk about light and pressure in AP2, but they are waves that exhibit simple harmonic motion. Now, some other definitions that you need is that you need to know that what a period is. A period is the amount of time required for one complete cycle. Periods are measured in seconds. Then we have frequencies, and these are the number of complete cycles in a period of time. They're going to be measured in hertz. Now on your formula chart, period is represented with capital T, and frequency is represented with the lowercase f. So you'll need to look on your formula chart and see if you can find those formulas. That there's multiple formulas that have period and frequency in them. Amplitude is another definition that we need, and it is the displacement from the equilibrium position. It's also known as the height of a wave when we're talking specifically about waves. So it is to measure the energy of an oscillator. So lots of times the higher the wave or the taller the wave is, the more energy it has. So we'll talk a little bit about that. And then also, the higher a pendulum swings from side to side, the higher its amplitude is, and also the more energy it has. So it'll be measured in different units depending on what objects we're talking about. Now, equilibrium position, you've heard me say this a couple of times in different definitions now. It's the center of the motion. It is where there's no forces. So if there were no forces, this is when it would be at equilibrium. So the net force would be 0, and this is in different spots. Like for a pendulum, that's when it's straight up and down, because there's no outside forces of the system working on it. There's only gravitational force. So that'll, so it's really where there's no restoring forces acting. Now the displacement is the distance between the center or your equilibrium position and the location of a wave or an oscillation at any time. A restoring force is a specific force, but it is exerted on a medium, whether that's a ball or a mass or a weight or whatever, to bring it back to the equilibrium position. Now with springs, we're going to talk about springs in particular first. The object to the left is a common spring system. It has a mass of some kind attached to the spring, and this spring is stretched and then released. This causes the entire system to oscillate. Now the spring supplies the restoring force on the mass, so it's going to pull it to where it comes towards it. And as the mass gets further away from the equilibrium position, the force upon it gets greater. There is no force on the mass at the equilibrium position, so once the spring is compressed in its natural position at rest, then there's no restoring force on it. So that's the equilibrium position. Something to realize, if you've ever been to one of those circuses or have been to like where they have bounce houses and stuff, sometimes they'll have something like a bungee cord that you run as far as you can, and then it'll pull you back. Well, that pulling you back force is known as the restoring force on a bungee. So that's the way to think about it. Now the equation, which is known as Hooke's law, and I believe Hooke's law is on your formula chart, is for spring is F equals Kx. And your F is your force, so it is in newtons. K is known as your spring constant, and it is actually going to be in newtons per meter. And then X is going to be your displacement value, and this is the displacement or the movement from the equilibrium position. On your formula chart, you'll see it as F of S, it's a subscript, and you'll notice that the force and the X value are vectors because they have arrows over them, and they're also absolute values, which means we aren't going to worry about a directional piece of information with them. Again, F is a force, so it's in newtons. Your spring constant, like I said, depending on what the spring's made out of, it's going to be newtons per meter, and your X value will be in meters because it's a displacement value. Now, if we stretch a spring with a mass and release it, it will oscillate. This is simple harmonic motion. But what is the period of this motion? Period, remember, is the amount of time it takes for one oscillation. So on your formula chart, there's also the period of a spring, which is listed as T equals 2 pi square root of m over k, where T is your period of motion, and it is in seconds. M is the mass of the body, and it'll be in kilograms. And then K will be your spring constant, which is in newtons per meter. So when we look at the actual units of what we're dealing with here, we have kilograms over kilograms meters per second squared over meters. So you end up with the kilograms canceling out, and you end up with the meters canceling out, and you end up with those seconds are on the bottom of a second, so it ends up that you have seconds squared, square rooted. So you end up with this being in seconds, this being in kilograms, and this being in newtons per meter. So that'll allow you to cancel everything out. There are some important things to notice about the equation. One, the larger the mass is attached to the spring, the longer the period will be, so those are directly proportional to each other. And then the stronger the spring, the shorter the period, and that's because the K value will be bigger, and so that'll make the overall value smaller. And then remember that the period is always in seconds. I did say that they're directly proportional. They're not directly proportional. They're directly proportional to the square of the mass. So because the mass is under a square root sign with the K value, it will be proportional that way. So let's talk a little bit about pendulums. They're the other main simple harmonic motion that we'll talk about. The object on the left is a pendulum. It's usually a mass hanging on the end of a string, and it could also be a mass on the end of a pipe or any other variation that's going to allow it to swing back and forth. Okay. Now, gravity supplies the restoring force to create the simple harmonic motion. So note that the higher the pendulum goes, the more gravity acts on it to bring it back to its equilibrium position. So I don't really like how this is listed. I think this is more your restoring force, and this is your tension force, and then you have your gravitational force. So we're going to be dealing with some, angles again, and we're going to be able to look at equivalent triangles. So the restoring force, again, for a pendulum is a component of the gravitational force, and it is tangent to the circular motion. So in most cases, your F of R is going to be mg sine theta because of the location on it on the actual triangle. So that should make it pretty easy because we've talked about tension forces, and so now we're just talking about those tension forces extended. But it is going to be tangent to the circular motion, and we'll talk more about that when we get into uniform circular motion. So the period of a pendulum is also listed on your formula chart with a subscript of a P after the T. and it is t equals the 2 pi square root of L over G. Now, your L value will be your length in meters, gravity is in meters per second squared, and then your period is again in seconds. So a way to think about it is if we have meters divided by meters per second squared, we actually have the meters get canceled out, and then we have 1 over second squared on the denominator, so that ends up becoming second squared over 1 and then square rooted. So that's how we end up with the period being in seconds. And then there are some important things to notice here as well with this particular formula. One, the period does not depend on the mass of the pendulum bob at all. Notice that mass is not involved in that. So I could have a giant pendulum bob, or I could have a little bitty one. It's not going to matter. And you're actually going to be able to do a lab that proves this fact. 2, the length and gravity are the only values that affect the period because they're the only values in the formula. So they will have a major effect on that. And then 3, as the length of the pendulum becomes longer, the period becomes longer as well. There are sections in your notes to put all of these things that we've talked about. And so, again, length is directly proportional to the square of the length the period is. So, but as it gets bigger, then the period will also get bigger. So, all right, hope this helps. Hope you've got those notes filled in so that all we have to do when we get to class is take examples and work those example problems. Have a great evening.